Let us look at what did we cover in the previous lecture, because the results from the previous lecture are very important and they connect well with the content of this lecture. So first of all, we looked at and learned that not every discrete time sinusoid will be periodic inherently. Rather, there is a condition, and the condition is that the frequency Fd, which is generating that discrete time sinusoid, has to be a rational number, has to be a ratio of two integers in order for that discrete time sinusoid to be periodic. This was the first observation. The second observation was that it is possible that discrete time sinusoids with different frequencies may generate identical waveforms. And we saw in postulate 2 of discrete time sinusoids that this happens when there are two different discrete time sinusoids having their frequencies separated by integer multiple of 2 pi's, and we have seen that such sinusoids generate identical waveforms. And the third observation was that the maximum rate of oscillation in a discrete time sinusoid occurred at Fd equals to half cycles per sample. So this was our observation. And based on these observations, because whenever we would like to play with any sinusoid, we would want that the discrete time sinusoids remain distinct. So they should be generating distinct waveforms for distinct frequencies. There should not be any ambiguity between the waveforms. And also we would want that when we increase the frequency of a sinusoid, then the rate of oscillation should increase. It is not a normal behavior to expect that we increase the frequency and the rate of oscillation starts decreasing. So looking at these problems and observations, we defined that okay, if we want to play with the discrete time sinusoids, then the rule of the game is that the frequency range for Fd for discrete time sinusoids has to remain between -1/2 and 1/2 cycles per sample. So this is what we learned and concluded the last lecture at this point. These are the readings from our previous lecture. We have covered till section 1.3.1 and section 1.3.2. And now let's look at what are the lecture objectives in this video. We will look at the basic structure of analog to digital conversion process, sampling, quantization, and coding. We will look very closely at the relationship between the frequency capital F, units hertz, of a continuous time signal, and frequency Fd with the units cycle per sample of a discrete time signal, and their connection with the sampling frequency Fs with the units samples per second. Then we will also look at what is aliasing, why does it happen, and how to avoid it. And lastly, we will look very briefly on how does this relates with the sampling theorem. Okay, a basic analog to digital conversion structure looks like this. An analog signal, XAT, first of all goes through a sampler, and once it is sampled, which is a process of converting a continuous time continuous valued signal into a discrete time continuous valued signal, it is converted into a discrete time signal. Then it goes through a process of quantization, and the output is called a quantized signal. And this quantized signal is then go through a coder, converting a discrete time continuous valued signal into a discrete time discrete valued signal, and the output is more of a like a bit stream, and this is called a digital signal. So in today's lecture we will be focusing on the sampling process, and although I know you know what the sampling process is, but there are a certain um, uh, properties and certain processes which we will look into detail. So we will be looking at the conversion of analog signal into a discrete time signal and associated topics related to the frequencies. Right, so let's go into the meat of the course of the lecture. Here we are about to start looking into the relationship between the frequencies capital F of a continuous time sinusoid, Fs sampling frequency, and Fd, which is the frequency of a discrete time signal. So we start by looking at a basic sampling phenomena, that whenever we convert an analog signal xt into a discrete time signal, which is called xn, we do this by taking samples of an analog signal every ts seconds, where ts is called sampling time or sampling period, and it is inverse of the sampling frequency or sampling rate. So mathematically this becomes that originally we have xat, and the t variable is now changed into n multiplied by ts. So this is xant's, and for simplicity we call this as xn, and n can be negative integers, 0, or positive integers. So essentially when we are sampling time t at certain specific instants, so there can be sampled at 0, 1 ts, 2 ts, 3 ts, 4 ts, and so on till nts. And on all these instants, whatever the signal value is there, we store it in xn in the form of x of 0, x of 1, x of 2, x of 3. So the signal values in discrete form are stored in xn, and we call this signal as the discrete time signal. It must be noted that, as I mentioned earlier, that ts is the sampling period and is the inverse of sampling frequency fs, and the units of fs are samples per second. Occasionally the units of fs are also called as hertz, but you should not be confused with the hertz. If it is being referred to along fs, then it has the same meaning as samples per second. Right, so let us begin by considering an analog sinusoid, which is mathematically described as cos 2 pi capital F t. Capital F has the units of hertz, and as we mentioned earlier, that when we are about to sample the signal, then this t will be converted into n multiplied by ts. Everything else remains the same. xt will be changed into xn, and this becomes cos 2 pi f n ts. And as we mentioned earlier, that ts is inverse of fs, so we can also write this as cos 2 pi fn over fs. Now if we recall from the previous lecture, the form of a discrete time sinusoid was xn is equal to cos 2 pi fdn, and comparing this equation with this one, I should have numbered the equations. then we find that FD is coming out to be equal to F over Fs. Now this is a very interesting relationship because it connects uh, all three parameters in one relationship. Fd, which is the frequency for a discrete time sinusoid, capital F, which is a frequency of continuous time sinusoid, and Fs is the sampling rate with which the continuous time sinusoid is sampled and is converted into a discrete time sinusoid. So the relationship we get to is Fd is equal to F over Fs. Okay, now let's very quickly look at the units. We know that the units of capital F are cycles per second, and the units of Fs are samples per second. So the units of Fd therefore will come out to be cycle per sample using this relationship, using which is defined here. The unit of F are cycle per second, unit of Fs are samples per second, and you simplify this and you get the units of Fd as cycle per sample. Okay, this is an important observation on the slide. From our previous lecture, we have seen that the frequency range for discrete time signals is Fd has to be between -half and half. And we also know that Fd is equal to F over Fs. So we can replace Fd here by F over Fs. So the range becomes F over Fs has to be between -half and half. And then we can multiply this entire expression by Fs on all three components. So it simplifies into that capital F has to be between -Fs by 2 and Fs by 2. Typically, the range for capital F we have seen earlier when discussing concept of frequency for continuous time sinusoids as the capital F has to be between -infinity and +infinity. But here we are seeing that the range for capital F is limited to -Fs by 2 to Fs by 2. The difference is that this frequency range of a continuous time signal applies only when we are about to sample a continuous time signal into a discrete time signal. So this is not a generic condition. This is a condition only for those continuous time sinusoids which we are about to sample into a discrete time signal. So if we want them to be sampled correctly, then this is the range we have to ensure. So what we will do is, first of all, we will look at the range of the frequencies in Hertz present in the analog signals, and we will ensure that the frequencies there are bounded within this range. If they are bounded within this range and then we sample these signal through some Fs and convert them into a discrete time signal, then there will be no issues and we will find that the resulting frequency Fd will automatically fall within this range. We will be looking at this concept in further slides as well, which will, I'm sure, clear this concept even further. So continuing from our previous discussion, just